We will now see two examples of parallelizing a computation, and the first is to introduce terminology, and the second is to see how we may want to change the computations in order to get the good performance on a parallel machine. So the first example is simulating currents in an ocean. And what we may want to do is to study the interactions between the oceans and the atmosphere. And we will look at the Atlantic, not at a very detailed level, but what we need to do is to simulate effects from the atmosphere, winds and friction when at the ocean floors and walls. And we can represent an ocean as a cross section, like a chessboard, with several chessboards put above each other. Okay, so the Atlantic is approximately 2,000 times 2,000 kilometers. That's a very rough estimate, obviously, but if we use that, it will be fine. Okay, so if we want to have 100 times 100 points in a cross section, that's one chessboard, so to speak, it will give us 20 kilometers between each point. But we probably want to simulate this as at a much finer granularity. Okay, so say that we want to simulate for 5 years, and we let each time step take 8 hours. Then we will need 5,500 time steps, and between each time step we recalculate the variables in each such cube. Okay, so the computations are enormous, but they can be parallelized, and the question is, at which level should we parallelize them? So now some terminology. A task is a unit of work that should be performed, and that is what we think about in software. I mean at the algorithmic level, not in syntax or in anything like that. Okay, and the tasks are performed in parallel with other tasks. And a thread is something which can run on a processor, and it works on one task at a time. Okay, processor is the CPU. I mean, I assume everyone knows what it is, but you will probably learn more in this course. So it's real hardware, and it executes one thread. But with modern hardware, with simultaneous multi-threading, each processor can have multiple software threads, meaning also hardware threads, in execution at the same time. So there will be one set of registers for each hardware and software thread. I mean, the software thread is what we think about in the program, and it will be using the set of registers for the hardware thread that runs in the core at the same time. I mean, at the moment. And for the Power 8, there can be up to 8 such threads, hardware threads. So what is really the purpose of simultaneous multi-threading? This is called hyperthreading in Intel terminology. Okay, well, we have a pipeline that can execute a sequential program, but it has more resources than usually are needed. So what Susan Eggers at the University of Washington and some colleagues to her, but it was she who run the project as the principal investigator, concluded is that instead of having usually too many resources and one thread executing without exploiting all of them, it can be better to have a varying number of threads in the same core. So when it is better to have 8 threads, it's better to have a simpler pipeline and more threads. I mean, each thread sees a simpler pipeline with fewer resources. And when it's only one thread that can run in the machine, it's better to give it all the resources. So it's, in some sense, a dynamically configurable pipeline that exploits the application that is running. Okay, so that's the basic thing about simultaneous multi-threading. We will look more into that later. So, now, the 4 steps in parallelizing a sequential program, and this is for any language. First, we need to identify the parallel tasks. In lab 1, we did that by saying that each node an actor should perform what each node needs. So the parallel tasks were the operations of one node. We can do the same for any other language as well, of course, but it's not necessarily the best. But the decomposition is to find a suitable number of suitable large tasks. That is an annoying remark, suitable number. And why? Well, what is suitable in one algorithm is not suitable in another, and what is suitable for the same algorithm for one machine may not be suitable for another machine. But it's still what we have. So we identify the parallel tasks, and next thing to do is to assign these tasks to threads. What does that mean? It means saying which thread should do which task, and that can be done in different ways. Okay. Now we come to source code as the 3rd step. Orchestration. That means managing all the communication, all the synchronization, and knowing which one computes what. So this is probably where we spend most of the time. Mapping is usually not done because it's automatically done by the operating system. Namely, that we want to say that this thread should run on this CPU. And these threads can run on any CPU, for instance. Okay, but usually we cannot, neither can nor want to control the program at that detail. And one reason for that is that the machine that we use typically not only runs one program, but other programs as well. Okay, so it's better to let the operating system decide when to do what. Okay, and partitioning, that's the most important part of writing an efficient parallel program, and that's what we do in steps 1 and 2. Okay, these 4 steps were introduced, or perhaps better to say popularized by in an important book written by Kaller and Gupta at Stanford and Berkeley. And also, sorry, I forgot one, namely J.P. Singh at Princeton. Gupta and Singh were at Stanford. They were professor and PhD student at Stanford University, and have done a lot of important work on parallel computers and algorithms, color as well. Okay, so let's move on.